Hello everyone, and thanks for attending this presentation. I am Alessandro Fornasier, and I'm going to present our work titled Equivariant Filter Design for Inertial Navigation Systems with Input Measurement Biases. This work tried to answer the following research question. Considering an inertial navigation system, how can we include input measurement biases into a geometric construction that we exploit to design better EKF-like filters? Essentially, there exist two different filter solutions that have been proposed for the inertial navigation system, trying to exploit its geometrical properties. The multiplicative extended common filter, which introduced an attitude error parameterization on SO3, and the invariant extended common filter, which is indeed a generalization of the MEKF that parameterizes the error on the symmetry group and is characterized by a linear aerodynamics whenever the underlying system is group affine. However, the inertial navigation system is not group affine when biases are explicitly included, and in general, most of the geometric solutions in literature lose the nice properties they are characterized with when input measurement biases are considered. This is the main reason why we tackled such a problem, and we try to find a symmetry that includes the biases and derive a filter with nice error dynamics. To achieve this, in this work, we first extended the classical inertial navigation system with a velocity bias extension. Secondly, we explored the semi-direct product between SE23 and its Lie algebra to define a symmetry group for the inertial navigation system and prove it being an equivariant system. And then we have made use of the recent theory of equivariant filter to design a filter that outperforms the state of the art. Let's consider the original inertial navigation system. We extended the original system with virtual inputs and a velocity bias. And then we have the magical machinery of geometry that allowed us to derive the lifted system on the symmetry group and the linearized aerodynamics. Here we have the linearized aerodynamics, which includes the navigation states and the biases, and on top of which we derive the equivariant filter. In particular, these are the matrices of the EQF, and it's interesting to note that both the error state matrix A and the output matrix C are mainly constant and state independent, with the only dependency of the error state matrix A to the origin input W0. But what does this mean? Practically, this is just a change of basis of the IMU measurement W from the estimated state to the chosen origin. Here we have some experimental results. In particular, we ran a Monte Carlo simulation and we computed the average RMSE for the first half of the trajectory to evaluate the transient performance, and for the second half of the trajectory to evaluate the asymptotic tracking performance of the equivariant filter compared with a MEKF. The plots show the transient on the left side and the asymptotic behavior on the right side only for the biases, but in general, the reduced linearization error of the QF translates in better performance in any states. In this other experiment, instead, we compared the robustness of the filters to wrong initial conditions. Interesting here is that even for huge initial error, not the logarithmic scales on the axis, the equivariant filter always converged while the MEKF failed for initial errors that are underneath the red area on the plot, showing the improved robustness of the proposed equivariant filters given by the nice linearized aerodynamics. This concludes my presentation. Thank you for your attention.